So we started talking about these inequalities, and solving these inequalities, especially by finding the key points, or what I call the key points, and then graphing them. And our answer is always going to be either along the x-axis or as an interval notation, set of parentheses or brackets. We use brackets if it's equal to, and we use parentheses if it's not. And we finished with this one on Monday. So the ones I want to look at next are these here. Now these four here are the exact same inequality, but they will have different solutions. Now one of the first things we can do with any of these here, we can start with A. 4x squared minus 12x plus 9 is less than 0. First thing we would want to do is factor it, because we want to find the key points. And when I mean key points, where it crosses the x-axis, where it intersects the x-axis. Because we're trying to see, is it greater than 0 here? It's less than 0. What values or parts of the graph are below the x-axis? So we could factor this here. Since 9 is positive, our signs are the same and match the sign of the middle term. So negative and negative. Our factors of 4x squared, well, we'll have x and x. And the factors of 4 are 1 and 4 or 2 and 2. Now the first one I would try would be 2 and 2. Then we can look at the factors of the third term, 9, which is 1 and 9 or 3 and 3. And I'm going to try 3 and 3 first. And if we check this here, 2x times negative 3 is negative 6x. 3 times 2x is negative 6x, which does indeed give us the correct middle term of negative 12x. Now at this point here, we could solve both of these to see where they equal 0. But since both of these factors are the exact same, we're really just going to get a point. So for the first one here, we can add 3 to both sides. Telling us that 2x is equal to 3. Divide by 2. Telling us x is equal to 3 halves. And we could do the exact same thing for the other factor. So, our main key number is 3 halves, because when x is 3 halves, the y value will be indeed 0. So, unlike some of the graphs that we had Monday, where we had 3 different spots, because we normally had, say, 2 places where it was 0, so we checked in between those 2 points in either side. Here, we only have 2 spots that we really need to check. So we need a number less than 3 halves. And what is a nice number that's less than 3 halves? 0, yes? 0 is a nice number. Especially when we're checking things in higher degree polynomials, 0 is a very nice number. And we need a number bigger than 3 halves, and we can just pick any number we want. So we can say what? 2. Yeah, doesn't matter. We just need 1. So 0 and 2. And from here, we will just check them. So we can plug into the beginning function. We don't have to do it in the factored form. 0, 4 times 0 squared, minus 12 times 0, plus 9, less than 0. Well, 4 times 0 squared is indeed 0. Negative 12 times 0 is indeed 0. So we get 9 is less than 0. Is this a true statement? No. We can do the exact same thing with 2. 4 times 2 squared, minus 12 times 2, plus 9 less than 0. Now at this point here, you don't have to do this by hand. 4 times 2 squared. We can plug this whole thing into the calculator exactly as we have it and see what we get. So I'll pull the calculator up here. We have 4 times 2 squared minus 12 times 2 plus 9. Enter. It is 1. Is 1 less than 0? Well, no. And we know at this point it is equal to 0, yes? So it'd be an open circle. So what part of the graph is, or what numbers for this are less than 0? Are there any? No. So this here is what we would call, say, the empty set, or no solution, because there is no point on this graph that is less than 0. Now what we could have also done, clear both of these out, is we could have taken 4x squared minus 12x plus 9 and graphed it. So graphing it does help because we can visually see that all the points are above the graph. And factoring does tell us that it is equal to 0 at the point 3/2, 1.5. So we can see all the points are greater than 0. So there is no solution for this here. Any questions on the first one? Now, what's the only difference between A and B? B is what? Equal to 0, yes? Now, we've already shown that the entire graph is above the x-axis, so there's really no points that are greater than 0. Or sorry, not greater, less than 0, yes? But at the point 3/2, it is what? Equal to 0, yes? So the only thing we could say about B is that we do have a solution, and the solution is 3/2. Because anything other than 3/2 does not work for this here, because all the rest of the points of this quadratic are above the x-axis. Now, if we wanted to graph it on a number line, it would just be the point at 3/2. Because anything to the left or right would be bigger than 0 on either side. It's both going to be greater than 0. Questions on any of this so far? We good with this so far, yes? Now, I'm going to skip C for now. I want to look at letter D. Now, we've already shown that the entire graph is greater than 0, yes? Every point's above it. And it does intersect the graph at 3/2, yes? So, greater than or equal to 0. 3/2. Well, we know that this point here is included, yes? And really just, not so much cheating, but just reutilizing what we've had before. We know when x is 0, 0 over here, it does give us a true statement because we had what, 9? Would be greater than or equal to 0, yes? So all the points to the right would be included, or to the left would be included. Here, if we chose 1, is 1 greater than or equal to 0? Yes. So we have all the points to the right and to the left because, again, the entire graph, except for the point 3/2, is above the x-axis. So we would have everything to the left of that point, everything to the right. And because D says equal to, we would also have that point. It's everything. Now, as an inequality, or as not inequality, but an interval, in interval notation, we would say the solution for this is negative infinity to infinity. It would be the entire number line. It'd be all of it. Questions on this here? Okay. Well, coming back to C, so if C and D, again, just like A and B are the same, it means all the points to the left, all the points to the right would be included because they are above the x-axis. But is the point 3/2 going to be included? No, because it's not equal to. Now, as an interval notation, we would say negative infinity, comma, 3/2, parentheses. Because this first part is saying everything to the left of the point 3/2. Union, 3/2, comma, infinity. Would be how we would have to write this here. Because unfortunately, we can't use some of the other tricks or shortcuts for writing this here. One of the shortcuts really is saying that we have the solution is the set of all real numbers excluding 3/2. We're just saying it's everything but this number here. Fortunately, we can't do that, so we'd have to write it out as this here. Questions on any of this so far? So inequalities are not too bad, especially when we graph them and we can start looking at those there. And even with checking points, I could have taken plugged it into the graphing calculator, gone second table, and looked at this here. So when we plugged in 0, when x is 0, y is 9. We have it. And we can say, okay, yes, 9 is either greater than 0 or less than 0. Greater than or equal to, less than or equal to. We can use this here. And we can use this to check points. Questions on any of this so far? Now, the other type of inequalities that we have are rational, fractional. And whenever we have these here, what we were really looking for are two main things, our key points. We want to find the key points of this inequality and go from there. So we find the key points, get points to check, and then see where the solutions are. Now, our key points lie in two main places, the numerator and denominator of our rational expression, the top and bottom of this fraction. Because we want to see what is going to make the numerator and what's going to make the denominator equal to 0. So our numerator is 2x minus 5. We want to see what's going to make it 0. And we also want to see what x plus 2, the denominator, is going to be 0. Now, if we look at the numerator first, we can add 5 to both sides, telling us that 2x is equal to 5. Then we can divide both sides by 2, telling us x is equal to 5/2. So there's one of our key points. As if the value of x is 5/2, the numerator will be 0, and if the numerator of a fraction is 0, then the whole thing will be 0. We also have to solve x plus 2. So the first thing we can do is subtract 2, telling us x is negative 2. This here is our other key point. And whenever I'm doing these here, and when y'all do these, it'd be good to plot these down so we can see what they are. So we have negative 2 and 5/2. Now, again, we're talking about this being less than 0. So 5/2 is going to have an open circle, because that will cause the entire fraction to become 0. We're not talking about it being equal to 0, so that has to be open. At negative 2, this here will always have an open circle. Even if it had been less than or equal to 0, at -2, it would have still been open. Because if x is -2, the denominator of this fraction would be 0. We cannot divide by 0. This is one of our restrictions when we talk about rational functions, rational expressions. So it can never work. But it is one of our key points. Because in most of the restrictions, these here, the graph is either going to stay above or flip. There's going to be some change occurring at this restriction. So we have all of our key points. Now we need points to check. So we need one that's less than -2, one that's between -2 and 5/2, and one that's greater than 5/2. So out of these three here, what's going to be a nice number to pick? 2? 0, yeah. If I can pick 0 as a point to check, I'm going to use it. 0 is a nice number, especially when checking. Now we just need to pick numbers on either side. So we can pick 5 and -5. And there's no real particular reason I chose 5 and -5. I just picked two numbers. We just need two other numbers to pick. And at this point here, we're going to check them. So we can start with -5. So we can say 2 times -5 minus 5 over -5 plus 2 is less than 0. Now again, at this point here, we could type this entire thing into the calculator, let it do it for us. If we did it by hand, 2 times -5 is -10 minus 5. -5 plus 2 is -3. So we have -15 over -3, which is +5. Is this a true statement? No. 5 is not less than 0, so we know the points to the left of -2 are not less than 0. They're going to be greater than 0. Now the next one we can try is 0. Now 0 is nice, again, with these here, because when we plug this in, 2 times 0 is 0. 0 plus 2 is 2. Is -5/2 less than 0? Yes. So the points between -2 and 5/2 work. And what that brings us to at the end is checking for 5. We want to see if 5 works. Now at this point here, we've done most of this by hand. I want to show you how to do this by the graphing calculator also. So we can start off with alpha, y equals enter. 2x minus 5 over x plus 2. So we have this entered into the calculator. Now we can go second table, and the x value that we want to check is 5. So 5 is 5/7. And this value here should be what? Less than 0, yes? Is 5/7 less than 0? No. So the only part of our numbers that works are the values between -2 and 5/2. So on a graph, we would shade this here as an interval. It would be the interval of -2, comma 5/2. Or what else we could have looked at is the graph of this here. Now it does show us we do have parts below the graph. The only spot we don't have is where it actually intersects the graph, which is at 5/2. But it does give us an idea of what's below the graph, what's above it. Questions on this here? We're going to do this one here. Now this one here is a little bit different because it is not equal to or less than or greater than 0. So one of the key things to doing this is for 1, getting it equal to 0. I believe we have 4x minus 5 over x minus 2 minus 3. Now, for this one here, we can start off by graphing it. So we have this graph here. And we're trying to see where it's less than 0. And for the most part, most of this graph is above the x-axis. It's greater than 0. Now, there's one key point that looks like it could be close to -1, where it is actually 0. And we could check the table and see. Error. So at -1, we do have 0, and at 0, we do have -1/2. At 1, we have -2. It continues down from there until we have an error at 2. So we do kind of see this solution set from there. Now, the way that we get there is, again, looking for our zeros here. What's going to make the numerator and denominator be 0? Now, we can see the denominator is x minus 2. So 2 is going to be one of our zeros. It's one of our restrictions. But the one place where the numerator was 0 was -1. Well, looking at this here, 4x minus 5, it's not going to be 0 there. And part of the reason for that is because of this -3. To really be able to see the restrictions, we need this as a single rational expression. But for us to be able to add or subtract rational expressions, we need the numerator and denominator to be the same for us to be able to add or subtract. So what that means for us is that we actually have to multiply 3 on top and bottom by x minus 2. And if we do this here, the first one will still stay 4x minus 5 minus 3 times x is 3x. 3 times -2 is -6. And if we distribute that negative through, we would get -3x plus 6. Well, 4x minus 3x is x. -5 plus 6 is plus 1. So we actually merge this thing back together. Our real rational expression, our single one, is that we have a numerator of x plus 1. We have a denominator of x minus 2. So if we want to find our zeros, we're going to set x plus 1 equals 0 and x minus 2 equal to 0. For the first one, we would subtract 1 from both sides, telling us x is -1. For our other one, we would add 2 to both sides, telling us x is equal to 2. And these would be our 2 key points, which the graphing calculator really told us that. Because at 2, it told us it was undefined, because again, it would be the denominator would be 0. That doesn't work. And at -1, we indeed have 0. Now for this function here, can we have this rational expression be 0? Yes, it says it is equal to. So at -1, we would fill that point in because it does work. But again, even though it is equal to, we don't fill in the 2 because the 2 would cause the denominator to be 0. We can't divide by 0. Now at this point here, just like we did before, we can pick points to check. 0, -2, 3. And plug those in and see, will -2 give me a value less than 0? Will 0 give me a value less than or equal to 0? Will 3 give me a value less than or equal to 0? And if we look on the graphing calculator, at 0, we get -1/2. That is less than or equal to 0. At -2, we get +1/4. That is not less than or equal to 0. And at 3, we get 4, which is not less than or equal to 0. This one doesn't work. This one doesn't work, but this one does. So we'd have all the points between -1 and 2. In an interval form, we'd have bracket -1, 2, parenthesis. Questions on any of this here? Questions on any of this so far? So hopefully you're seeing that a lot of these inequalities, especially with these functions, do have some complexity to them. But once we get to the, ironically, the key points of them and see what those key numbers are, there's not a whole lot to them. Interestingly enough, the last one that we're looking at this is this one here. So this one here, we do have two inequalities. And the best thing to do with these here to start off with is to get them equal to 0, or get one side to be 0. It doesn't matter which way we go, because I could subtract the 1 over x minus 2 from both sides, or I could subtract the 1 over x plus 3. Well, I'm just going to subtract the 1 over x plus 3. It really doesn't matter which way we go. Because here, the right-hand side will become 0. Can we subtract these two fractions from each other as they are? Well, no. We have 1 over x minus 2 minus 1 over x plus 3. Now, one thing we know for sure is that we will need key points. We're going to need some key points to be able to tell where the graph's most likely switching from the or above the x-axis, below the x-axis, which points are going to work. And two spots that we know for sure is x minus 2 and x plus 3. Because these cannot be 0. So I could check those. X minus 2 is equal to 0. X plus 3 equal to 0. So here I can add 2 to both sides, giving us x is equal to 2. Here we can minus 3 from both sides. X is negative 3. So we have 2 and negative 3. And we know even though that this is equal to, both of these points are going to have open circles because, again, they're the values that are going to make the denominator, the bottom of the fraction, be 0, which do not work at all, even if it is, hence here, equal to 0. Now, working this out by hand, the next thing we'll need to do is see what's going to make the numerator be 0. But the only way we can see that is if we have a single rational expression. So we need to get the denominators to be the same. Well, for the one on the left, it doesn't have an x plus 3. So for us to be able to add or subtract, we need to multiply top and bottom by x plus 3. The one on the right is missing an x minus 2. Because if we multiply these, the denominator is going to be x plus 3 times x minus 2 in both cases. And this is still greater than or equal to 0. Now the numerator, we're going to distribute. We're going to multiply x plus 3 by 1, which is nicely enough x plus 3. We'll do the same thing for our other fraction. We'll multiply 1 by x minus 2, giving us x minus 2. Now at this point here, we can subtract the two numerators. So we'll have x plus 3 minus x minus negative 2 is the same as plus 2. And what's x minus x? X minus x is 0. So those two will cancel each other out, leaving us with 3 plus 2, which is 5. Is there any way to make the numerator be 0? Is there any way I can plug a value into the numerator and make it be 0? No. So if there was, we would find out what it is and add it as one of our key points to check to see where the graph is above greater than 0. So, nicely enough, we only have 3 spots to check. Negative 4, 0, 3. Now in the graphing calculator, we can say 1 over x minus 2 minus 1 over x plus 3. And this here was our original function, yes? Once we moved it over, got it equal to 0, we could say graph. And we have this here. And again, we're wanting to see where this graph is greater than or equal to 0, is above the x-axis. So at negative 4, we get a y value of 5, 6. Is that greater than 0? Yes. So these points work. We can check our next point, 0. 0 is negative 5, 6. That does not work. And our last one is 3. Well, 3 is positive 5, 6. So that one does work. So we'd have all the points to the left of negative 3 and to the right of 2. And as an inequality, or not an inequality, as an interval, we'd have negative infinity to negative 3 at the union of 2 comma infinity would be the entire solution set. Any questions on any of this here? Any questions on anything we've gone over so far? And really that's it. That's all we have for these here. And we could use the graphing calculator in conjunction with these intercepts, or these key points, to find it. Now, again, with this last one, we were able to find 2 of the key points just from graphing it. Now, if I wrote it as our final single rational expression, we could do this and hit graph, and you'll see that the blue line that we had from the 2 parts is covered up by the one in red, so they are the same. And another way to verify it was that we can say second table, and if we look at all the values for y, we get the exact same. So if you're not sure that you got it condensed correctly, you can always plug it into the graphing calculator and see, are the y values the exact same? As if for some reason that I got 4 instead of 5, second table, we can see that the y values don't match up anymore. There is an error somewhere, that they're not the same anymore. Any questions on any of this here? Now, we're going to stop there. We'll do 3-4 tomorrow, 3-5 Friday, and that'll be the end of chapter 3. I will also have the review sheet ready by then so that you can have it also.